All right. Okay. So let's do some review. What is the difference between heat and temperature? Heat moves is energy. Actually, I should say this right. Let's say it right. Heat is energy that moves from warmer substances to colder substances, like the heat that moved from the metal to the water. Temperature is a measurement of average kinetic energy. There are two different types of energy. So heat is not really, it's just a substance that moves from hot stuff to cold stuff. And temperature is a measurement of that substance that is transferred, right? What is specific heat? It is how many joules are required to raise 1 gram of a substance by 1 degree. How can specific heat be determined? Using Q equals mc delta T. What is the equation for specific heat? Well, we just mentioned it. Q equals mc delta T. Identify the variables. So Q is energy. Also can be called delta H. M is mass in grams, and I'll put that in parentheses. C is specific heat capacity. In joules per gram degree centigrade. How many joules for 1 gram, 1 degree centigrade, right? And delta T is temperature. Delta T temp. And you can use kelvins or Celsiuses. It doesn't matter because they are, if 10 degrees Kelvin is 10 degrees Celsius, or the transfer of 10 degrees is like 273 to 283 Kelvin is the same as 0 to 10 in Celsius. So the delta T doesn't change. It's still 10 degrees. How much heat is absorbed by 250 grams of aluminum if its temperature increases from 85 to 15? So it is final minus initial. 85 minus 15 is 70 degrees. And its specific heat capacity is 0.897 joules per gram degree centigrade. And that's going to tell me the energy when I multiply all that stuff together. So 250 times 0.897 times 70 degrees is 15,698 joules. I rounded up. That is my answer. What is the specific heat of a metal when you have a 12.5 gram sample? And I'm going to make C just C instead of X. I'll just call it C. And we raise it from 19.5 to 33.6. So 33.6 minus 19.5 is 14.1 degrees Celsius. And 37.7 joules of heat were transferred. 37.7 joules. So what I have to do is multiply these and divide that answer by that answer. So 37.7 divided by parentheses 12.5 times 14.1 close parentheses. You got to put stuff in parentheses or it will try and do order of operations for you. So my answer is 0.2139, etc. joules per gram degree centigrade. A sample of water absorbs 5860 joules of heat. The temperature of the water increases from 20 degrees to 40 degrees. So 40 minus 20 is 20. 20 degrees is my delta T. Specific heat of water is 4.184 joules per gram degree centigrade, a very high specific heat. And they want to know what is the mass. So I need M is what I'm solving for here. Again, same process. Multiply these two together, divide that answer by that answer. 5860 divided by parentheses 4.184 times 20 degrees, 70.03 grams. That is my units there. The on your own stuff I'm not allowed to touch. That has to be an on your own sort of thing, unfortunately, because I'm using the entire guide here, the entire review. So usually I strip that stuff out. This time I did not. What is an exothermic reaction? A reaction where energy moves from the system. Remember, the system is basically the styrofoam cup or the beaker or whatever, to its surroundings, or the environment is also what that is called. What is an endothermic reaction? What happens to the system when in an exothermic reaction? Generally, that's like a beaker getting hotter, but I don't like to think of things in terms of getting hotter and colder. I like to think of whether energy is coming out or energy is moving in. An endothermic is a reaction that absorbs energy, and you'll feel it as a cold beaker that absorbs, because that's heat transferring from your hand to the beaker. Absorbs energy from its surroundings. Surroundings into the system. It's a positive delta H, or energy as a reactant. Energy as a reactant. And I guess I should put that up here, that an exothermic is a negative delta H, and energy as a product. So I'll leave those answers there. Oh man, I'm gonna do this on your own part, because this has two things that I really need you to understand. Identify reactants and products. So this is reactants. This is products. This is reactants. This is products. Change in heat, or delta H, that's the difference between reactants and products. I'm just going to put it outside here. It doesn't matter whether it's outside or inside the curve. It's delta H. This one's going to be negative. This one's going to be positive. Exo or endo. This is exo. This is endo. And I'm going to go ahead and label some other things. So this, from the reactants to the top of the hill, is E sub A, also called E sub A equals activation energy. And I'm going to be very specific. I'm going to say forward, because the reverse activation energy goes from the products to the top of the hill. So it would cut off right about there. And again, here, from the reactants to the top of the hill, E sub A, activation energy. And at the top of the hill, the activated complex. Again, activated complex. I know I'm overkilling, but this is important stuff. All right. So exo or endo? Well, if I'm a solid and I'm going to a liquid, if I have ice cubes out, and then we'll assume we're in the North Pole. I'm at the North Pole and I have ice cubes. What do I need to do to get that to turn into liquid? I have to add energy into the system. So this is endothermic. If I'm going from a gas to a liquid, then it's the opposite. I have to pull energy out of the system. I have to pull energy out of the gas That's what a cold cup does. It pulls energy out of the liquid water gas or the vapor water gas that is around your cup and makes water on the outside of your cup. It is exo. Negative delta H, mentioned it up here. Up here, a negative delta H is exothermic. Energy as a reactant, endo. Energy as a product, exo. All right, I'm gonna stow all this Hess's law, and I'm going to do this one right here because honestly, it's the maximum difficulty that you should have on this at this particular juncture. When you get into AP Chem, we will do all kinds of Hess's law practice, but we have a little more time to do it, and we're a little more focused on it. Instead of it being part of a unit, it's really its own little practice thing that I have you do. So what I do is I look at the target, and this is the target reaction, and I need 4 NH3s. Well, the only place I see NH3s is right here. So I'm going to have to flip this reaction. So I'm going to flip it, and I'm going to multiply it times 2 at the same time. So hopefully that doesn't confuse you. So I have 4 NH3s going to 6 H2s plus 2 N2s. And that gets rid of this reaction. But remember, anything I do to this reaction, I have to do to this number. So I have to flip it, which is making this negative number positive, and then I have to multiply it times 2. Okay, so now I have 4 NH3, so I'm going to circle those. Now I need 5 O2s. Well, I'm going to have some combo of O2s here. I know I'm going to have to multiply something else. So I'm just going to wait on that for the time being. We're just going to leave that one for now until we get it. Maybe we'll get it when we multiply all these other things. So here I need 4 NOs as a product. I have 2 NOs, so I'm going to multiply this times 2. And I'm just going to put a 2 in front of the N2, a 2 in front of the O2, and a 4 in front of the NO. And then I'm going to make sure that I put a multiply times 2 out here beside my my equation so that I know that I need to multiply that times 2. Now I have my 4 NOs. I'm not worried about the O2s or the N2s yet. I'm just looking for the things that are in my target. Here, I need 6 H2Os. Well, here's the only place I have H2Os. At least they're on the right side. So I need to multiply this whole thing times 3. And so what I'm going to do is just make this 6, and this 3, and this 6, and then I'm going to multiply this times 3. Now I have my 6 H2Os. Now the rest of this has to cancel. So everything that's not circled, and by the way, if we go back to my 5 O2s, look what I have. I have 2 O2s here and 3 O2s here, and they're on the same side, so they do not cancel. They become my 5 O2s. Now those N2s and those H2s need to cancel. So I have 6 H2s as a product and 6 H2s as a reactant. That doesn't exist. I have 2 N2s as a product and 2 N2s as a reactant. That now doesn't exist. So now all I have is the stuff that's in my target reaction. So negative 180.5 times 2 is negative 361. 91.8 positive times 2 is 183.6. And negative 483.6 times 3 is negative 1450.8. And now I'm going to add all these together. Negative 1450.8 plus 183.6 plus a negative 361 gives me negative 1628.2 kilojoules. That is my answer right there. I don't want you to work on all these other squirrely ones. If you need any more Hess practice, look at the worksheet I gave you. That's all the Hess practice you need. Okay, down here to a heating curve. Label the heating curve below, include states of matter and phase changes. All right, the bottom of the heating curve is only solids. The second slope of the heating curve is only liquids. The third curve of a heating curve is only gases. That must mean that the phase changes occur on the flats. Indeed, they do. So if I'm going up the heating curve, that is melting. If I'm going down the heating curve, that is freezing. And again, on this flat, if I'm going up the heating curve from liquid to gas, that is vaporization. If I'm going down, that's the outside of your cup again, that is condensation or condensing. That is all the states of matter and phase change, but I'd like to add some stuff. I'd like to say flats, potential energy. Slope, those are kinetic energy changes. You can tell the temperature is changing. Here's the temp, it's going up. Kinetic energy. All right, let's keep moving forward. Okay, what is happening to the heat energy being added? Oh man, I'm stepping on your own again. 1, 3, and 5. Well, I kind of said it. 1, 3, and 5, you're changing the kinetic energy. So that's what's happening to the energy that you're adding by heating it up. Kinetic energy, potential energy. I think that's what they're getting at. Yeah, that's all they're saying in the on your own, and I already did it in the not on your own. So, what type of reaction results from the absorption of energy to break bonds? That is endothermic, and it is a positive delta H. Now I'm going to change this because you don't release energy from bonds breaking. Bonds breaking requires energy at all times. It doesn't make energy ever, 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 ever. Bonds forming. What type of reaction results from the release of energy due to bonds forming? That would be an exothermic reaction. You get the hint that both things are happening in a reaction. You're breaking bonds and making bonds, and whether it's overall exothermic or endothermic depends on how big that number is. It is a negative delta H. So if I create more bonds than I break, then it's exothermic. If I break more bonds than I recreate, then it's endothermic. I'm breaking one bond here. Well, this is energy on the product side. So this is energy being released. Here I see energy on the reactant side. So this is energy being absorbed. And are bonds being formed or broken? Both. Yes. That O2 is being broken, and then you're reforming a bond with Mg and O. That's what I mean. You're breaking bonds and forming bonds usually all the time. Are bonds being formed or broken? Yes, both. You are breaking the CO3 up to make a CO2. You are reforming a CaO from that. So yes, let's just put are bonds being formed or broken? Yes. Are bonds being formed or broken? Yes. I'm going to go ahead and go down here. Are bonds being formed or broken? Yes. You have to break into an O2 bonds to make NO, but they put energy on the reactant side. So this is endo, the same as the one above it, energy on the reactant side, endo, N2. The energy is going from outside the system to inside the system. Endo, positive delta H, positive delta H. This is negative delta H. Okay, what is collision theory? Collision theory says that 3 things have to happen for a reaction to occur. 3 things must occur for reaction, RxM. First, you have to have a collision. If you don't have a collision between particles, you won't have a reaction. Second, they have to have the right orientation. If I'm doing an O2 and an H2, they have to hit perfectly right in order to make a water, in that the 2 H's have to hit one O, not both O's. If they hit them straight on, that's not the right orientation. And third, I must have the right amount of energy, or activation energy, right amount of energy. That would be the activation energy. What is activation energy? The hill of energy required to get over to get from reactants to products. Excellent. Activation energy. And we've drawn it enough by now that you know it's from the reactants to the top of the hill. That's it. And the reverse is from the products to the top of the hill. So it depends which way you're looking at it. But either way, what are the three requirements? Well, I just said in collision theory what the three requirements are. So, and I identified all the labels, included the activated complex. Go back to the reaction diagrams, and that is an endothermic. The products have less energy. Products have more energy than reactants. Where'd that energy come from? It came from outside the system to inside the system. In order to get up here, you have to add energy. What is a catalyst? How can it increase the rate of reaction? By lowering activation energy. It is a substance that speeds up a reaction. Does nothing to equilibrium, nothing at all. So if I had activation, let's say I have this exothermic reaction right here, what a catalyst is going to do is going to give me a shortcut to use less activation energy, which means the reaction happens far faster because you have a larger group of molecules that have that energy than that energy. So that is what it means. What are the 5 factors that can affect the rate of reaction? That's going to be concentration. That's going to be surface area. That's going to be temperature. That's going to be a catalyst. What is my 5th one? Concentration, surface area, temperature, adding a catalyst. Oh my God, what am I forgetting here? What am I forgetting here? Oh man, I hate forgetting stuff. Let's see. Let's take a quick look. 5 things to speed up reaction. One of these is just not in my head right now. Concentration, catalyst, temperature, surface area. It's not nature of reactants, is it? 5 ways to speed up a reaction. Hang on. Heat it up. Increase concentration. Divide and conquer particle size. Dropping in a catalyst. Oh, they don't have a 5th thing. I think they mean the nature of reactants here. Like I could use a more reactive reactant, I think. These are the 4 that you really need to pay attention to. Concentration, increasing concentration speeds up a reaction. Increasing surface area speeds up a reaction. Increasing temperature speeds up a reaction. Adding a catalyst speeds up a reaction. What changes in concentration, temperature, and surface area will increase? Well, concentration goes up. Temperature goes up. Surface area goes up. If you increase any of those things, you're going to increase the rate of reaction. What changes in concentration, temperature, and surface area will decrease the rate of reaction? Well, if I lower the concentration, that's ridiculous to ask that. Lower the temperature and lower the surface area. Now, the lowering the surface area is the one y'all get confused by. Like a cube has less surface area than a powder. You are increasing the surface area by making the particles smaller. And I think some of y'all get that kind of backwards in your noggin. But do not get that thing confused. When you decrease the size of the particle, you're actually increasing the surface area. Okay, you can go through those. It's just asking you if I chop firewood into smaller pieces, it makes lighting a fire easier. Why? Because you've increased surface area. Like you can go through all of that and figure it out. If you have any questions before the test tomorrow, don't hesitate to ask me. I'll be here in the morning, or you can ask me before the test, no problem. What is chemical equilibrium? It's when the forward reaction rate is equal to the reverse reaction rate. That means if I have two H2s plus an O2 going to reversibly two H2Os, every time an H2 and an O2 combine to make two waters decompose into H2 and O2. That means the forward rate and the reverse rate are the same. It doesn't mean I have equal amounts of these things. That is not what it says. What is Le Chatelier's principle? A system at equilibrium, when disturbed, will try to regain equilibrium. And it will do that by making more products or making more reactants or whatever it has to do. How can changes in concentration affect the chemical equilibrium? Increases in concentration, equilibrium shifts away from. It runs to the other side. Remember, the dividing line is the arrows. So if this side is increasing concentration, then it runs to this side. If this side is increasing concentration, it runs to this side. An increase in concentration, equilibrium will shift to other side of reaction, or forward or backwards. Whereas a decrease in concentration is the opposite. Equilibrium will shift towards a decrease. How can changes in temperature affect the chemical equilibrium of a reaction? Well, again, it's just another substance. Heat is a reactant or product. And you know that it's a reactant or product. So if it's on the product side and I increase it, a reaction runs left to the reactant side. If it's on the reactant side, it's an endothermic reaction and I increase the heat, then equilibrium shifts to the product side. That is how that works. How can changes in pressure affect the chemical equilibrium of a reaction? Increase in pressure, and I'm talking about overall pressure, not increasing the pressure of one gas. If you increase the pressure of one gas, you're increasing the concentration of that gas. Increase in pressure will shift equilibrium to the side with less moles of gas. And by that, I mean you're looking at the coefficient. Make sure you're not including energy. You just need to look at the side of moles with gas. So catalysts, no, they do not affect equilibrium. And then a decrease in pressure, again, it's the exact same thing. A decrease in pressure will shift equilibrium to the side with more moles of gas. And I think we're about to look at that in 2 seconds. Yes. So here, I have NO is added. NO is a reactant. Make sure you're looking at the identical thing because this is not N2O, it is NO. So if I add a reactant, equilibrium is shifting right. System is cool. Here is heat. It is on the product side. It is decreasing the concentration of a product. If I decrease the concentration of anything, equilibrium shifts towards that. So reaction is cooled. N2O is added. That is a product. When I increase the concentration of a product, it runs to the reactant side. Pressure is increased. Well, here I have 2, 3. There's a 1 here. So 1, 2, 3 moles of gas on this side, 2 moles of gas on this side. So if there's 2 moles of gas on the product side, when I increase the pressure, it's going to run to the product side. H2 is removed. Well, it's the exact opposite of increasing a concentration. Equilibrium shifts towards decreases in concentration. And since H2 is a reactant, it's on the left side of the arrow, it shifts to the left. H2O is removed. Here I'm removing a product, so the exact opposite effect. NO2 is added. That is a product, so running to the left. Pressure is decreased. I have 2 moles of gas on this side, 1 mole of gas on this side. I am decreasing pressure, so it's going to shift to the side with more moles of gas. NO2 is removed. I am decreasing the concentration of the product, so it's going to shift to that side. System is heated. Heat is on the reactant side. That means I'm increasing the concentration of a reactant. Equilibrium is shifting to the right. N2O4 is added. That is a reactant. I'm increasing the concentration of a reactant. Equilibrium is shifting to the right. System is cooled. Exact opposite. I'm removing the concentration of heat from the left side, so equilibrium is shifting left. We are not playing with equilibrium constants or equilibrium expressions. That's it, guys. 31 minutes. Not bad for 6 pages or whatever. And I might have gotten into the do on your own now. I will see you guys tomorrow. You have a great day. And if you have any questions, don't hesitate to come in here in the morning and ask me, or come in here on during the test, before the test, and I'll answer anything you have last minute. All right, guys. I will see you tomorrow.